Welcome to Micro's CSP Zeitgeist.
Micro Zeitgeist.
That's right. We might even get some spillover into the audience from Zeitgeist.
Yeah, you came here to hear Al. You got the other Al.
That's right. So on October 16th, the Green Renewable Energy and Policy Seminar Series will host Taliver Heath from inside Google, and he's going to talk about power usage at Google. Today, we have Dr. Al Yuen from Sopogy. He's had a 20-year career in technology, research and development, and manufacturing, most recently serving as the general manager of Coherent Semiconductor. He was the vice president of sales and marketing of MCore Corp, which makes triple junction cells for the solar industry. He spent 12 years at HP, where he authored Bill and Dave's Memos, a book based on the culture and writings of Bill Hewlett and Dave Packard. I'm sure those are for sale on Amazon.
That's right. I've got a whole collection back there.
He attended the University of California, Berkeley, where he received a BS in EE, and at the University of California, Santa Barbara, where he received his MS and PhD in electrical engineering.
Great.
So thank you, Al.
Thank you. Thanks, John. Okay, are we good, Tiffany? We go? All right. All right, so thanks, John. Thanks to Google for inviting me. We'll try to plow through it. There's lots of interesting stuff to talk about. It's going to be micro CSP, generation of electricity, heating, and cooling. And let's see if this works. So today's talk outline, we're going to talk about key takeaways, technology versus product. Kind of a solar tutorial. You guys are probably all experts, but when I give these talks, you'd be amazed. Little things like CPV, PPAs, all that, just kind of get everybody on the same plane as far as different types of solar technologies. And then what I always like to do is, as a startup for solar, just really talk about kind of bridging our product development through HP and all these different types of technology companies in the Silicon Valley on how to really get things into the product life cycle. And I think it's important, maybe interesting to Google audience as well, and then a summary. All right, so about us. All right, so we were incorporated in 2006. This is really quick. We're headquartered in Honolulu, Hawaii, venture-backed. Really originated, a lot of resorts there obviously needed heating, lots of laundry. You can imagine at hotel, resorts, cooling for Hawaii, and then electricity generation. So they came to the founder, Darren Kimura, at Sopogy and asked him for one solution for all of that. And so that's kind of how it all came out. And we do electricity generation, cooling, air cooling, heat, process heating, whether it's water treatment, desal, laundry, anything. Can go up to 200 degrees C. And then this last symbol is just really a hybrid of any of those systems. So you can do tri-generation from one system. We just launched our SopoNova 4.0 during Intersolar a couple months ago. So that's going well. And simply what we do, we provide total solar solutions for industrial commercial market. There was a question before, boy, those collectors seem kind of big to put on a rooftop at home, and that's exactly correct. We actually target industrial applications, and the reasons for that will be obvious after the presentation. So why Hawaii? I guess it's a dumb question. Hawaii is a fun place, but very expensive, right? Because everything has to be shipped in, flown in. So it has, as far as baseload pricing for gas, natural gas, easily 2x that of mainland and much higher than in other areas. So that's one. The other is because it's kind of remote and it's expensive, the governor started an initiative at the beginning of this year that said by 2030, Hawaii wants to get 70% of the whole island's energy needs from renewable sources. So it's really big push, pretty big bogey out there. And then finally, tons of support, obviously, from Congress, Senate, local government, local in the state of Hawaii that's really pushing it. So it was a really good place to incubate, lots of application, fun to go to business trips with. We never have any trouble getting vendors to fly out, so it works out that way. So how do we differentiate? So when you start out, you're a startup, you don't know your name, people don't know how to, it's Sopogy, what is it, you know? How do you differentiate? And so we really looked at starting from as simple as water heating, generation, and air conditioning to how can we make a big difference. And so we really started targeting distributed generation because we really feel that instead of grid tied, and there was plenty of people that were doing extremely large applications in parabolic, central receivers, other types of technology, 50 megawatts really and up. I mean, typically it's really 100 megawatts and up because it doesn't make sense to do all of the site preparation, et cetera. So we started targeting it's kind of smaller, anywhere from several hundred kilowatts to tens of megawatts, is what we say. And that's in the generation side. And then that exploded to, can you use some of the heat to do process heating and then air conditioning? So kind of finding a niche, but as you'll see, it's a very large market niche. How does Sopogy, and I'll go over this and then we'll go into more of the technology, but the business works as we really want to be the system provider. Some people want a total solution, which is turnkey energy, but we want to do the technology, supply, be the manufacturer of that, and then work with project financing. Of course, everything needs the financing to work, and then local contractors that we will qualify and certify to do that. That's kind of our model. So let me back up a little bit on what I talked about as far as technology versus product. So as John pointed out, I've been in Silicon Valley many years, grew up walking through cherry orchards when I was little. And a lot of what technologists in Silicon Valley like is the fact that it's technology. People are enamored with technology. But at the end of the day, it's really the practical implementation of that in a product. And I think that's the key focus of what our company does, what we're trying to do with solar technology. So back in 1879, Edison didn't really invent the light bulb as everybody thinks. He actually made the first commercially practical one that actually lasts more than a few minutes or maybe an hour in the lab. So it made it practical. And then that was what people used for 100 years, basically. And people still use that when you go into houses. It's about 20% efficient as far as electricity going out, and what comes out is light. And then a little while ago, people went into the fluorescent lighting, which is much more efficient, but pretty bulky. You know, industrial applications, Costco, large garages, et cetera. It wasn't until 100 years later, imagine that you actually got to a more efficient light bulb, CFL, and that's slowly moving. And so what I'm saying is that things move technology into products that really affect things in a much bigger way. It takes time to do that. So commercially and practical is really what people are looking for. And I think everybody can create your own, what does it mean to be practical? What does it mean to be commercially available? But really the commercial available product development is much more key to solar or any of the products that we generate in Silicon Valley than just kind of the technology. So quick tutorial just to kind of get everybody on the same page. You guys know about solar. You got lots of solar in your parking lot. Solar starts with what everybody thinks of when we say solar technology. It's a solar cell, solar panel. Starts with a semiconductor-based silicon, SIGs, copper indium, or copper tellurium, thin films, all of those you've heard about. Essentially uses the photovoltaic effect, generates a current. The current directly to run anything DC or through a converter, inverter, go into a more AC, and also ties into the grid, right? So that's photovoltaic thin film electric effect. The issues with PV, or solar panel type of things, is it's done with very large clean rooms, right? When silicon went into more of a 12-inch or 300 millimeter, we thought, wow, I mean, how many microprocessors and transistors can you fit in on this 12-inch? You know, it was almost like a big pizza pie, and that was a big deal when we were in the semiconductor industry. But if you think about solar, we talk about it in certainly acres, if not square miles. And then you begin to kind of realize just the daunting effect of how do we get semiconductor of any kind, spin it on, spray it on, paste it on, just dump it on. It still has to cover square miles of this to be effective as a real energy solution. And this is really the issue as far as the solar cell photovoltaic PV type of technology. And I've been in that at HP and then at MCOR for many years. So why am I looking at more on the CSP side, solar thermal? For a lot of these regions, because of the limitations really on the size and scope of PV. So since that's so expensive, and I see the EI solution out there that you have, but a lot of people say, well, let's use less silicon. Let's have optics that shrink, 500 suns, 1,000 suns. I think there's a crazy company in Hollywood that says 2,000 suns, all that. Great stuff. But anyways, it's trying to use less silicon, but then you hope that the full-on 2-axis tracking, the optics and everything on top of that is cheaper than actually just using the silicon underneath. And actually, it works throughout again, commercially practical and all of the aspects of that. So that's CPV, so concentrated photovoltaic, again, trying to use less semiconductor for that solution. So then we get to solar thermal. Again, around the world, you say solar thermal, everybody, at least in Europe and Asia, thinks about these flat panels that heat water or pool, et cetera. And of course, that's a big industry in itself. But what we do is we do concentrated solar thermal. And it's a little bit indirect than the photovoltaic effect, and that is it heats up some kind of liquid, generally goes into a steam, runs a turbine, and then it goes into electricity. So it's a little bit more displaced from that. Different types of CSP. Now we're getting into concentrated solar power in the solar thermal regime. Has to do with troughs, which are parabolic troughs. Again, rays come in, focuses on a central beam. Dish, again, it's a large, looks like a large satellite dish. Again, concentrates at a point. And then tower, which EI and some of the other e-solar companies do that as well. And again, lots of heliostats that are all focusing the sun's radiation on a single tower point. And these are all CSP, concentrated solar power. Then at the end of the day, you have a source of very large square miles of collectors, again, trying to reduce that cost. Goes into some kind of storage, again. And I'll talk about more about the storage. It goes into generally a power block, generator, and then eventually onto the grid transmission on that. And these are very large scale. PG&E you read about. Certainly Spain is doing all these. These are in the 100 gigawatt types of scale on that. But that's kind of the basic CSP. So why CSP? So what I've shown here is hours during the day. This is the solar day, typically. And this sometimes is the demand, certainly for countries like India that are quite hot, or even in regions of the US. People go home and they turn on their AC. So the peak may not be just during the day hours, but in the evening hours when they go home, it's still hot. They start running their dryers, doing all they do at home. So the need actually can peak beyond the sun days, all right? So if you look at PV, if a cloud comes by, it doesn't really store, because storage right now from an electricity point of view is still quite expensive. I think that'll get solved. But right now, it's intermittent. If it's generating, it's generating. If it's not generating, it just goes down to zero, and it'll kind of spike out. So this is what we would call in the utility non-firm energy, where you can't predict it and it's firm. It's basically spiking. Wind, same way, right? Typically, you put it into a windy place. For sure, it's not going to go down to zero. But wind, as you know, fluctuates. And the amount of generation, and I exaggerate, but it'll fluctuate, and it's not firm. And you don't store the electricity, because it's very difficult to store the electricity. And there's people looking and working on storage. So the whole solar thermal, why people are interested in that is it does give you a good, firm energy. And the reason why that is that heat, especially in a large tank, or the amount that you're running through your solar field, doesn't, just because you turned off the spigot on your bathtub, doesn't make it cold instantaneously, right? So in essence, it has a thermal inertia, if you will, that guarantees that it's relatively firm until you actually turn it off, then slowly it cools down, right? So you do have some natural storage and inertia, and it gives you a nice firm energy. And then storage then is in the form of tanks of water, oil, and some people are talking about molten salt for very high temperature, but relatively reasonable as far as cost and implementation. So let me introduce you to the hurdles, right? So I want to talk both on the micro CSP, but also kind of putting on my technology to product hat as far as making something commercially available. What are the hurdles you have to do, right? So I'm assuming that the technology is interesting, it's easy to implement and all of that, and you've completed your product design, which is a big assumption, because typically people who start companies are technologists. They love to tinker. It's never done. If you just give me another month, I'll give you these other features, right? So it's always creeping. But let's say you have a design freeze, beta, and it's done. Then you have to go into various hurdles that take you finally to market acceptance and product introduction into the field. And even though we've seen a lot of nanosolars and thin films and CPVs, very few of them are really commercially practical. Not just commercially available where, if you're, for example, the Tesla, great. right? You target a very high-end, not necessarily commercially available, but it has to start out at a certain market, and it's just beginning to roll out. So commercially practical is really the key. So let me back it up a little bit. When we do hardware design of any technology, every product, and even at Google, when you're doing product, when you're selling product, it certainly has a certain life to it, or service to it. Starting from the concept, what I talked about, the design freeze, and then obviously launch, release, commercially available. And then people, large companies like Google, probably HP, GE, they do this really well. Startups are constantly learning this process, a lot of times reinventing the wheel, taking it through all of these. So you're not here at the product release looking at, hey, we didn't think about certification. We didn't think about qualification. Or, oh, I didn't know people were going to put this on the roof. And when the wind blows on it, actually it pulls things off where it weighs much heavier than if there wasn't any wind load. So lots of stuff had to be thought out. And then end of life, certainly products run out of lifetime. Is there another follow-on services, et cetera? And these are, again, very quick gloss over the life of a product. So let me get back to the micro CSP, that CFL slide that I presented to you earlier. CFL took many years, but it went from a proven industrial fluorescent type of technology. Again, people believed in fluorescent lighting. It wasn't something where you go, oh, trust this is a new technology. It's not going to be poisonous or anything. People understood it was just a large fluorescent bulb twisted in a many small way and made it a compact fluorescent. So it was proven technology, but this wasn't exactly something you could displace in the residential area or a residential socket. So it took a while, but it's a drop-in solution. And that's what we're seeing with micro CSP. This large CSP, desert type of applications, Solar One, all of those have been proven for decades. They've been running for 10, 20, some 30 years. And in fact, parabolic type of technology has been around for probably 1,000 years since Archimedes tried to, I think, burn ships out on the shore, right? So parabolic troughs, proven, et cetera, but not something that you could drop in like a CFL into an industrial application today. And that's why we went with a micro shrunk down CSP that has all the benefits and proven capability on the CSP, but small enough where you can really use it as a point of source, put it right next to your boiler, which is your current socket, which is gas fired, and then just be a solar source of heat that goes in. And so traditional CSP, so what are some of the issues there? You've looked at, obviously, Osra. A lot of the others startups are in discussion in the news all the time. Very large, most of it with glass. Osra uses glass. Everyone else uses big glass types of thing. Again, 20, 30 feet up in the air. So you're not really talking about anywhere near residential or industrial, et cetera. You need lots of land, wind loads, et cetera, and just a lot of complexity as you start looking at that. Certainly, there's a space for that and a market for that, but as far as the industrial application, pretty difficult. So we got to the kind of more of a Goldilocks effect, which is photovoltaics we thought was not big enough, too small for what we wanted to do, didn't do process heating, and again, didn't do air conditioning as what we wanted to do for the resorts. Traditional CSP, too big because you needed this land. It was transmitted away. A lot of the people that we were talking about, industrial needs in India, China, or around the world, don't have very good transmission infrastructure. So that was out of the picture. And so right in the middle is just right, which is just the right size to be big enough for industrial applications, be able to do process heating, and then also do solar air conditioning. So meets this tri-generation requirement and has enough oomph to go into the tens of megawatts for the electricity as well. Again, 3 different types of applications here. Efficiency overall, the most economically practical is really taking solar heat, if you will, and just using it as heat, because that conversion can be extremely high. And for typical flat panel, when you're doing pool heating on a non-windy day, it could be 80, 90% evacuated tube. So those are very high applications. It doesn't go up to the high temperatures that we need. But again, 60% is really good for solar thermal, getting 200 degrees C that we can use. Yes, Kevin, question?
Efficiency based on land area or reflector
this is efficiency based on energy, solar coming in through a measure, and then what is the thermal energy going out. So it's not just essentially a kilowatt comes in, 0.6 kilowatt of thermal goes out.
So on the reflector as opposed to the lamp itself?
The system, correct, yeah. So the question was, what is that efficiency? And that efficiency is calculated energy coming in from the sun, energy going out in thermal. And then, so every time you do a conversion, of course, you start losing efficiency. Every time you're converting from thermal to steam to turbine, et cetera, and generators. All right, so very quickly, I wanted to get back to how people use the energy up. This is relatively old data, but oil continues to dominate, gas, coal, obviously, hydroelectric, and then you have renewable, as you all know, is pretty small. But the interesting thing is, right, if you look at this chart here, kind of a spread of US energy and the way it's divided up, you'll notice very quickly that residential is about 21%, more than 50% industrial. The rest of it is plane, trains, automobile type of fuel use. Right? So there's a big, big application in the commercial sector. Right? So that's one. Right? So that's a great market. Now, if you move it to what do they need that energy to do, if you look at it, I just underline the ones that use heating and cooling. Right? So when you start looking at electricity, because everybody's enamored with electricity, everybody in Silicon Valley and all the people talk about generation and grid tie and feed-in tariffs. Reality is there's a lot more people that need cooling, heating, refrigeration, water treatment, desalination. All of those applications is a huge, huge market. And that's only in the US. And imagine a lot of the non-industrialized, India, China, Middle East, as far as water treatment, all of those agricultural, the heating and the cooling are huge in those areas. Right? So again, just to point out that that market, which people do not necessarily look at, is a huge need. And displacing that energy really has a huge impact than just electricity. Okay, so how do we add value besides shrinking it down? Okay, fine. You took a big CSP, you shrunk it down, it's much smaller, we get that. Well, one thing is we ship it flat. So I'll pass this around. It's not, basically, we can make this is one of the pieces in the parabolic, it's a rib, that's what we call it. It's kind of a body type part. So it's a rib part that forms the parabolic. It's highly precision stamped. But this is just a standard aluminum stamping. You can go anywhere in the world, and they'll be able to just stamp this out. So we can go into a region. We are completely fabless. Speaking of silicon and semiconductor PV fabs, we don't have any fabs anywhere at all. We go into a region. We give them the stamps. Right? They take it. They stamp these out. They bend it to form these ribs. And I'll pass that around. And these ribs just slide around on those posts, aluminum posts, to form the, you're seeing here, they just sit into these little guides. The posts go in. They put the backing on. They turn it over. They put the front, that's an Alinod polished aluminum surface on the top for the reflector. Put it on the stands, and then it's ready to go, right? So it's, we ship it flat. If there's any shipment, if it's not locally produced, it's completely shipped flat, like an IKEA flat box. We assemble it locally, so we create the local jobs, which regions like India, developing regions really like that, because it's not just some really high-tech thing that just comes in, it's something that they can produce locally, assemble locally. And then it's modular enough, something not necessarily as small as the one in display, but 3 times as big as that, where you can get kind of distributed generation, scalable, modular. Question?
So the mirror is thin and it just bends to form the ribs?
Yes, the mirror is about 1 millimeter thick of aluminum sheet. It's polished, anodized, and then has a high reflective protection layer on it. And it's cut out in sheets. There's 3 sheets on each one. 3 of these sheets sit onto each collector. And at the end, and I can show you more after the talk outside, but basically they're just put on, and the 2 cowlings on the ends push the 2 ends of that reflector down onto the ribs to force it to take that parabolic shape. It's really important to take that parabolic shape, because that's what you're getting the concentration when the sun comes in to focus on that 1-inch tube. So there's a collection tube that's 1 inch, 60 inches of overall space as far as the sun collection.
So in the field, you're able to form it with the necessary accuracy?
Yeah, it's basically a pretty flimsy film, not film, aluminum sheet. But as you put it on and you push the cowlings down on it, it begins to form right into that shape. And you'll see it out there. All right, so no transmission issues. Again, distributed generation, which India loves. A lot of, again, getting back to some of those regions. What we see the future is really a whole new generation of distributed power supply, power plants throughout the US. So again, speaking of that, so all these ribs are inside, turned upside down, obviously, and these very inexpensive aluminum posts just guide it, essentially. And then you'll put the you put the backing on. The backing is necessary there in case there's inclement weather, hail, etc. It'll stow itself upside down. Let's see, I think I need to click this here. So basically, it's a single axis tracking, very simple algorithm there. At night, it'll stow upside down. During the day, it tracks the sun. During the inclement weather, there's a weather station locally that'll power up and say it's either the temperature, wind, or humidity, or some web-based. We can web-based control it, and it'll turn it upside down to protect it. In the evening, it stows upside down so that there's any dew or collection of special dust, et cetera, that goes on. The other is, in some of our fields, we'll have just an automatic sprinkler underneath so that if it does need to be cleaned periodically, it can be automatically sprayed while it's in the stow position. Again, trying to keep the operation and maintenance costs down and just essentially be automated. So with this type of, again, getting back to the gentleman's question early on, rooftop mounting, et cetera, we had to do a lot of analysis, a lot of wind tunnel testing, et cetera. It's really like an airplane wing. If you look at that, people look at it and they go, wow, this is an airplane wing. So it does have a lot of structural analysis that's needed. Again, deformation obviously is the worst case, is how much can it handle before the aluminum starts buckling. The other is, as you have certain wind loads on it, how much structural pull, either downward force or upward force, needs to be calculated so that when they build it into a rooftop, they need to know exactly. It's not just, it only weighs about 200, 250 pounds because it's aluminum, quite light. But with the wind, and as it starts pulling down, it can be much higher than that. So a lot of the analysis has to be done in order to be okay. Another of the hurdles, obviously, is field testing. And we're just beginning to do that. We just launched the product. We have multiple rows. Again, it's Sopo Nova. Whenever you hear a startup that has Sopo Nova 4.0, that means they've been busy for the last few years doing 1.0, 2.0, and 3.0. And we were just honest enough to admit that this isn't the very first collector we made, even though it's the first product commercially available. So we've done various versions in the field testing. Hawaii has very salty air, good storms that come through that really test the product. We had to go through, just like Edison did, a lot of different films that just don't work very well. I mean, aluminum loves to corrode. It oxidizes very easily, and Allenau, we found, is the company in Germany that specially makes it. So a lot of research just to find something that doesn't corrode after 20 years, or again, if it does, we can pull it off. But hopefully we don't have to do a lot of that. So rooftop labs. And then we found the mobile labs and obviously regional demonstrations to be really key. Anytime you're doing a new technology, whether it's based on old CSP, but new enough where people really have to see it. And so all of these are available, and we try to bring it to different sites to do that. Okay, so just recently, if you actually live in the area, we just gave a free one. Eichler, it's an old swim and tennis over in Palo Alto. We just gave them a free one. You can go back there and take a look at it. It's just a small 8-foot collection for their heating needs there. But again, trying to make it available, demonstratable, and field tested, so it's actually practically available. The other in this area, as you guys get to know and work in the energy field, lots of different certifications. Obviously, you heard of UL for safety. TUV is something that is mainly a lot of European-based. And then CE certification, obviously, is. And these take a long time. And in fact, when you're doing something as new as we do, CE and TV, well, TV doesn't even have a certification for us. So we're part of their committee to write a certification for CSP. CE, all of their test lab assume yours is only 4-foot panel sections because all they do is PV. So we've come in with our section. They don't know how to test it, so we have to work with them on the equipment. So just a lot of little hurdles when you're working with startups, when you're trying to get down to 2 cents per kilowatt hour. There's just all these little hurdles that you have to get through, besides the obvious. So ramping up manufacturing, again, initially what we thought was this is really easy to make, right? Really easy to assemble. In fact, we were doing it in our shop floor and putting it in. But what we found out is if you don't have the right jigs to do it, when you turn it around, there's a lot of moment of freedom there, and it'll actually become this kind of potato chip thing, because even though you've stuck all the pipes in, you've put all that stuff in, it tends to have a lot of freedom there. So what we realized is you have to have some pretty good jigs in order to hold it all together, put the tension wires in, and lock it down so that it's nice and solid and clean. So all of these things, I won't bore you with it, but again, ramping up manufacturing is more than just building one. The technologists love to build one, they move on to the next thing. Building thousands of these, shipping them across the ocean to Dubai in the desert, and then working through customs and getting all of that. There's just a lot of things, aspects of that. And then obviously the market acceptance side, what we talk about when we work, a lot of it is evangelizing, and we give a lot of talks. But because of our outsourced nature, we're fabless, so we don't have any manufacturing, and we really don't have any crew, if you will, that goes out and installs. So we'll certify, and so we have what we call parachute teams that'll go in throughout the world and help train the local EPCs, engineering, procurement, and construction type of companies to do that. So, and the key takeaways that we've been trying to do with micro CSP is enables a new generation of scalable distributed. Again, we want it to be scalable, modular, distributed generation. It's a total solution, and we're trying to target that pretty large generation space of industrial, commercial that we talked about, electricity, heating, and cooling. And then one thing that I really liked about the technology when I went in from more of the PV world is it can be fabless, locally made almost anywhere because it's just sheet metal, on-site assembled, and then drinking water, water treatment, all of those things. It enables a lot of very interesting things that we generally don't think about when we're looking at just kind of energy generation, which is kind of the focus of people. All right, I think that's it. Nope, that's it. Thank you very much. Any questions? Yes. Yes, well, you can use different types of absorption chillers, and some of them are based on ammonia or expansion. There's adsorption and there's absorption chillers, and so I'm not an expert on that, but pretty large systems that are condensation-based or compression, pressure-based, and they essentially work with process heating right now with a boiler that's connected to it, and then we'll just come along and provide the heat source from a solar heat source.
So if we go back 3 years and Google decided to deploy this technology instead of its 9,000 solar panels, so we have, I guess, 1.7 megawatts of just electricity, no heating or AC, grid tied. How would life be different had we gone with this solution?
Well, if you go back to that slide, I would imagine you use more. For Google, is probably, I would say, you don't probably have too much servers and stuff here, but office buildings would have a lot. Up to 10-20% of air conditioning that you could have displaced. It's probably not electrical air conditioning, I would imagine, in some other form. Would it displace air conditioning as well? Whatever process heating you use is probably just hot water and on the cooking side, and the electricity. How much? Do you know how much acres or land that's being used for the 1.7?
Well, I
you don't know.
9,000 panels.
9,000 panels. 1.7. Right.
Size, and they're all either on roofs or carports.
Right.
There's nothing on the ground.
Yeah, so for the campuses that are built obviously strongly like this, again, not residential, but I would imagine these are cement or I-beam type of structure. We've built these in India that are based on rooftop. Once you get into more places like Bangalore, even the land there is quite expensive. So they're going on rooftops, but it has to be a certain grade of rooftop, which typical buildings. So to answer your question, how would it be different? I think you would solve some of the other potential heating as well as cooling needs, as well as electricity generation. And I'm not sure about certainly the cost. I think this gentleman had some questions on cost. Cost is obviously can be all over the place depending on the size of it. But our manufacturing costs, certainly in Asia, we start looking at that. We're really talking about a few $100s of collector. It's again aluminum, bent again, made locally, so the collector is extremely inexpensive. Most expensive part is probably just the polished aluminum sheet on that. And then the rest of the cost, third of the cost, is really on the power block. I didn't talk too much about it, but we're working with a company that uniquely does very low temperature hydraulic engine based on the expansion of liquid versus a steam base, which changes water into steam, taking a lot of energy to do that. So it's much less inefficient than if you expanded small piston volumes of water, essentially, just using the expansion of water, which has a lot of power in order to drive a generator. Yes, Kevin?
Is your heat transfer fluid the same in every application?
Yeah, so again, because it started out as a resort type of application, needed to be very safe, and that's why we use a food-grade mineral oil. It can get into the drinking water, it can spill out, nothing happens. It had to be that because it was around Hawaiian resorts, et cetera. So it's the food grade. And the reason why we use, obviously, a transfer fluid is because we don't want it to go to steam. We want to go to 200 degrees C without having to deal with high pressure steam. Once you get into steam, the cost of the plumbing, the piping, the people handling it goes way up. Any other questions? Yes, John? I can repeat the question too.
I know that the Central Valley agriculture business uses a lot of hot water and steam for food processing. Are you selling anything into that market?
Good question. So where else do you need heating and cooling, right? Here, Las Vegas is one. We're talking to a lot of people in Las Vegas as far as the cooling and obviously energy side. Great sun, et cetera. And then all along the San Joaquin Valley, the heating, all the way up to Napa, where we're looking at cooling for the wineries, et cetera. So quite a few of those projects. They're not announced just because they're not fully, we're doing all the financing, all the things that we're doing. But yeah, absolutely, we're doing a lot. And then back in Hawaii, again, macadamia nut drying, because it's actually a fruit nut, and it has to be dried in order to be edible in the way we see it, as well as pineapple drying. So there's a lot of mundane type of stuff that need a lot of energy, and we're working on all of those heating applications.
I have one more. What kind of temperatures and at what powers can you generate in your system?
So temperatures is 200 degrees C. Again, it's lower than the super large CSPs that go up to 3, 4, maybe even 500 for the super steam. And that's one reason why is that we don't use that much heat, because we're trying to run the hydraulic engine between 95 degrees just before steam generation, steam conversion, and whatever the ambient is, 25 degrees, 30 degrees C. So it's 200 degrees C is what we focus on. And that's why we went to the micro and still could do that. So that's one question. The other is how much energy does it generate? So we tend to target what we see that makes sense is really between hundreds of kilowatts to 25 megawatts of power. It can go bigger, but I think once it gets bigger, it's just not practical. Distributed generation, then you're talking about, hundreds of acres of land, and you might as well go to the really large CSPs, which probably have more of an economy of scale on that point of view. Yes.
Could you tell us about one of your great success stories in Hawaii and what it would take to translate that into great success in the Sunbelt states here?
That's right. Okay, the question is, it's a great success story. So we just launched it. We have a very small project, a 500 kilowatt in KSP, and it's at NELHA, which is a natural energy lab in Kona. Right? So we're just putting that together, and that should be up and running in the matter of probably a month, 2 months. And then we've got actually Hawaii, again, getting back to why we started in Hawaii, there's a large 10 megawatt plant that's in the planning stage that we're working with them. The state is funding it through bonds, et cetera. So that's probably our largest ones. And then lots of the smaller ones in the US, mainly on the process heating and air conditioning, because it's a new technology. The other stuff isn't available. PV is prevalent on some of those. And then unfortunately in the US, large plants are kind of at a standstill because of the ITC. Everything, all the proposals are out, and everybody's kind of just, tapping their fingers on the desk, waiting for this next regime or whatever happens, in order to really get to the large 10, 20, 50 megawatt type of plant sign off, because nothing's going to get done until that thing gets approved in order to, or extended for 2008. So a lot of our activities actually in Europe, and I spoke of India for cooling, heating, as well as electricity generation. So all of those are in the planning stages and going through.
Well, related to that, so you said you donated a setup for a local swim club. So
what costs are they displacing, and how much would it have cost them had they paid for it?
Yeah, it's great. So one collector displaces about, what we calculate as far as the rate is about $4,000 a year, which is not tiny as far as their heating, as far as their water treatment needs. And I think in 1 year it displaces about, I don't know, I think it was about 17,000, I think it was 17,000 metric tons of carbon as far as one of the collectors do that. But I can get you the numbers for that. And then if we just kind of donated. It was Clinton has a program where if they're really trying to encourage a lot of industry to kind of look at projects almost like a Habitats for Humanity. So we put 100 hours of labor and our own collectors and everything, and put it in as far as our commitment to the Clinton Foundation on greening as part of that.
Anything else? I guess you'll be available to answer questions.
Yeah, I
out
have
by
some
yourself?
pamphlets
Oh,
here if
yeah,
you're
right.
interested.
Right.
Please pick one up. And then you can always email me, or again, any questions. Bruce also is our local manager that's around. I run the international and all of the operations on the mainland. But if you want to come out to Hawaii and visit the plant, we're always welcome. Thank you for your time.
Thanks, Al. Thanks, Bruce.